a problem. Gravitational force is the force that keeps the universe together. That means it's a universal force. It acts between planets, between stars, between the earth and the sun, between everybody seated here. There is a gravitational force. There's also gravitational force inside the atom, between the electron and the proton, between the proton and the neutron. So it's all over. It's universal. It's all over, and it's a complete force. And this force was got by Isaac Newton. We know that it is Isaac Newton who got this. And there's a story behind that he sat under an apple tree, an apple came down. He started thinking about why is it coming down. Well, the idea is he started thinking. If it was us, we'd have opened our mouths and swallowed it whole and said thank you. But he thought about it. From there, we got Newton's law of gravitation. 1687, that's the year. And his thesis was published. It's called Principia. Sir Isaac Newton, this British scientist, he has many inventions, and you'll hear his name many times. And according to the law of gravitation, every particle in the universe attracts every other particle. See, that's powerful. Every particle in the universe attracts every other particle. But this force is proportional to the product of their masses, and inversely proportional to the square of the distance between them. Okay, I'll let that run by fast. So the force increases according to the product of their masses, and it's inversely proportional to the square of the distance between them. So if you have two masses, m1 and m2, and the distance between them is r, then the force is given by caps G, which is a constant. It's called the universal gravitational constant. The product of the masses divided by the square of the distance. Now, this universal gravitational constant was found by a scientist called Cavendish. We know it has a value 6.67 times 10 to the negative 11. How do we get those units? You simply get those units by rearranging this to take this to the left-hand side. You know this will go up, right? And m1, m2 will be in the denominator. When you put all their units, you're going to get Newton meter squared on top by kilogram squared in the denominator. So that is Newton's law of gravitation. So before we go too far, let me ask you this simple question. If the distance between two masses is doubled, what happens to the gravitational force between them? How many times is my question? Don't say small. It becomes 1/4. All right, let me add something. What if the distance between two masses is doubled and the two masses are also doubled? What happens to the gravitational force? Stays the same, because the two masses were doubled. You have a 4 in the numerator and 1/4, right, in the denominator. So that's the law of gravitation. Now we have to connect the gravitational constant caps G with small g. They are completely different. One is the acceleration due to gravity, isn't it? 9.81. The other is a gravitational constant. Do you think there's a relation between the two?
Yes.
There should be a relation. We're going to find that relation between the two. And it's a simple thing to find the relation between the two. So I called it gravity at the Earth's surface. So you consider that there is an object, that's the Earth. You consider that there is an object at the surface of the Earth. That is the radius of the Earth, right? That's the radius of the Earth. And there is an object here. Let's say its mass is small m, and the mass of the Earth is me, mass of the Earth. The radius of the Earth is re. Can you tell me the force exerted by the Earth on this mass? How much force does the Earth exert on this mass? See? If I ask you what's the weight of the object, you would have told me. What's the weight of the object? Oh, I've got to take that back now. What's the weight of the object? The mass of the mg. M times small g, right? Now, what do you mean by weight of an object? It's nothing but the force exerted by the earth on the object, which we could find using Newton's law of gravitation, couldn't we? So now we have two ways of representing the force on that object. One is using its weight, the other is using the law of gravitation that we got now. So I'm going to put both of them together. On the left-hand side, you have the weight of the object. On the right-hand side, you have the same force represented using the law of gravitation. The masses cancel out, and you get this wonderful formula. Shows you that the acceleration due to gravity is related to the gravitational constant, isn't it? Surely, it's related. They're not the same, of course not. They are related. And it also tells you that if the radius is smaller, now we are comparing planets, right? Let's imagine a planet which has a huge mass and a very small radius. What do you say about the acceleration due to gravity on that planet? A big mass and a small radius. Must be bigger. So what do you know about the density of that planet? If it's a big mass in a small radius, you know the density is higher. So we come to the conclusion that the more dense a planet is, the greater the acceleration due to gravity. That's where we start thinking about black holes. And I'm sure you've heard about black holes. Black holes are so dense that the acceleration due to gravity goes to tremendous values that the light that the star sends out is sucked back into it because of the huge gravitational force. So it's a star, but the density has become so large that the acceleration due to gravity is big enough to take back light into it. That's why we call it a black hole. But another thing that tells us about this is that if you look at the Earth, does it have the same radius at the equator as at the poles? Is the Earth completely spherical? Is it a perfect sphere? The answer is no. It's flat at the poles. In case you didn't know it, it's flat at the poles. So the polar radius is slightly smaller than the equatorial radius. Are you with me? So where do you think the acceleration due to gravity would be bigger? At the poles or at the equator? You see, it's the same people listening, it's the same person talking, but you need to put me off. Okay, so if the radius is small, and where did I say the radius is small? Poles. Therefore, the acceleration due to gravity at the poles is like 9.82. But at the equator, it's 9.79. You have that small change. Okay, another reason for the change in acceleration due to gravity would be the spinning of the Earth. Isn't the Earth spinning on its own axis? Yes. And I'm not talking about the Earth going around the sun. I'm talking about the Earth spinning on its own axis. Now we know there will be a centripetal force, isn't it? And what's the formula for centripetal force? mv squared over r, but we also had another way which is better. We wrote it as mr omega squared, didn't we? So the omega, the angular speed of the Earth, no matter where you are, is the same. What is the angular speed of the Earth? The Earth takes how many hours to make one rotation? 24 hours. So you can get, and the angle is 2 pi radians, isn't it? So the angular speed of the Earth is 2 pi divided by 24 hours. That makes sense? And no matter where you are, the angular speed is the same. Centripetal force depends not just on the angular speed, it also depends on the radius. You see that? So if you are on the equator, let's say you are here at this point, you are far away from the axis. You know the axis is a little bit tilted, right? Okay, you're far away from the axis. But if you're here, you're very close. Are you getting what I'm saying? Therefore, where would the acceleration due to gravity be a little bit smaller? Will it be away or closer to the axis of rotation? At the equator? We'll find this, okay. I gave you two factors, we'll find it. The third factor, if you make a hole down in the earth and go down, do you think the acceleration due to gravity would change?
You're getting closer.
Okay, let's say that you make a hole that's big enough to take you to the center of the earth. I don't know how you know whether you reach the center. Let's say there's a flag there, and you get there, okay. When you get to the center of the earth, what do you think the acceleration due to gravity would be? Very high or very low? I'm asking you, what is the acceleration due to gravity at the center of the earth? At the surface, same as at the surface? No way. Would it be zero? Yes, it is zero. I'm going to prove that it's going to be zero at the center of the earth. Why? Because as you go further down, there is less and less mass that's attracting you, isn't it? Because you don't care about the mass that's above you. You only care about the mass that's below you. Are you listening? So if you get to the center, how much mass do you have below you? Nothing. The sphere gets smaller and smaller. Okay, another factor. As you go up from the surface of the earth, will the acceleration due to gravity change? Okay, how does it change? Does it increase or decrease with altitude? Decreases. So now we have come to the conclusion that the acceleration due to gravity is maximum at the surface of the earth, which I'm going to prove mathematically. You go down, it decreases. But again, there's another question. Where is the decrease going to be faster? Is it when you go higher? I'm just making you think. Is it when you go higher, or is it when you go deep into the earth? We have to answer all those questions. So anyways, acceleration due to gravity depends on so many factors. I gave you at least 4 factors. Let's try to find the mass of the earth before that. Whoever thought about mass of the earth? I mean, how do you find the mass of the earth? It's a joke. But you can take the earth and put it on a triple scale. Couldn't we use this to find the mass of the earth? Just rearrange this formula? Because we know all those. Do we know the radius of the earth? How do you find the radius of the earth? How do you find the radius of the earth?
Measure the curvature,
Huh?
I'll say if you can measure the curvature of the circumference.
Correct. You measure the circumference and divide it by 2 pi. That's how you find the radius of the earth. You move over the equator, right? Get the circumference and divide it by 2 pi. You get the radius of the earth. It's about 6,370 kilometers. So you put that in meters, you put the value of g, put caps g, and you're going to get the mass of the earth. Let's see what we get. 6,380, according to where I got it from. When you put all those numbers, you're going to get the mass of the earth. See what we get? It's about 10 to the power 24 kilograms. 5.98 times 10 to the power 24 kilograms. That's the mass of the earth. And I was teaching this one time and somebody asked me, does that include the mass of the buildings? Does that include the mass of the buildings? Well, we have not created anything. We just dug them up. So, of course, it includes everything. The only difference is we took it from underground, refashioned it, and put it on top. So, tell me that day when we create something, and I'll rethink all my philosophies. Until that time, mass can neither be created nor destroyed. Energy can neither be created nor destroyed. Momentum can neither be created nor destroyed. You have so many conservation principles. We're getting to all that. We will learn all that. Okay, so that's the mass of the earth. By the by, does anybody know the mass of the sun? Now, we are in this business of finding the mass of every star, knowing the distance of the earth from each one of them. That's what physics is about. This is just the beginning. The mass of the sun is 1,000,000 times more than the mass of the earth. It's 10 to the power 30 kilograms. That's 1,000,000 times more. But yet, the sun is made up of only gases. No kidding. Just think about it. It's just made of hydrogen and helium, not solid material like the Earth. And yet it has a mass 1,000,000 times more than the mass of the Earth. Are you thinking? Do we know the temperature of the sun? Yes, we do. Do we know the temperature at the core of the sun? Yes. It's 10 to the power 7 Kelvin. 10 million Kelvin. Did we have to go to the sun to calculate that? Not necessarily. That is physics. Do we know the temperature at the outer edge of the sun from where heat and light is coming out? Yes, about 6,000 Kelvin only. So as you go from the center of the sun to the surface of the sun, the temperature changes from 10 million Kelvin to 6,000 Kelvin. Welcome to my world. And let's go back to this. So physics is about the universe, studying everything. Did I mention first how gravity changes with altitude is so easy? I'm not going to show it to you. Let's see whether you can give me a formula for that. If you go up from the surface of the Earth by a height h, okay? Can anybody give me the formula for the acceleration of gravity at that height? Because we already have this, don't we? Don't we have this?
So would it be R minus H?
R?
R minus H plus H?
Now decide. Decide. That was R plus H. So would the formula be G is Gm by Re plus H the whole squared? Right? That's all. Finished. Why do we take time on that? That's all. So that's how the acceleration due to gravity changes with altitude. Nothing big. I did not even have to draw a diagram for that. I'll just roll slowly so you don't feel we're going fast. Okay, which is the highest place on the Earth?
Everest.
Does anybody know the height? That's going to be in feet or something. About 8 kilometers. Which is the deepest ocean, by the by?
Should be Pacific.
Pacific Ocean. What's it called? It's called the Mariner's Trench. Trench, right? 11 kilometers deep. So the lowest point is 11 kilometers deep. The highest point is about 9, not 8, 9 kilometers high. So the difference is 20 kilometers. I wanted you to see that. That's our Earth. Got it? But just notice this. When you put that number in here and calculate G, you are surprised, isn't it? It's almost the same, isn't it? You've gone up by 9 kilometers, but yet G is 9.77. That's a change of 0.3%. You got it? So it doesn't change that much with altitude. I want to ask you this. Look at this formula and tell me, at what height would G become 0? At what height, what number would you have to put in here? So,
When the height is equal to the radius of the air. Oh no, what? Sorry.
I'm talking about altitude. We're not going down, we're going up. How high would you have to go so G is 0? That's what I'm asking you.
Where there's no more gravitational pull.
I mean, what height is that?
There's always microgravity.
What do you mean by microgravity? He has a point.
Well, I mean, there's always a gravitational pull somewhere.
So,
Doesn't matter where.
no, we're talking about only the gravitational pull of the Earth now. Oh, you're considering everything. No. Just imagine nothing else exists. Only the Earth. How high would you have to go? So G, small g, is 0. Now, this is why we've taken time, and I like this. Come on. You can't. If you look at it and you know math, you know this has to be infinite for this to be 0. What am I trying to say?
And
That means you never escape, practically, you never, or theoretically, I mean, you never escape from the gravitational field of any planet. But practically, it almost gets to zero when you're at a certain height, isn't it? That makes sense? Okay. So that is, now, if I ask you, how does gravity change with depth? Can you give me the formula? As you go down. I'm quite sure you're going to say, and most of you said it, I'm quite sure, you just said it, you said, just put RE minus how much you go down, right? Which is absolutely wrong. And tell me why. So gravity at a depth, D. That's the Earth. We are trying to find the acceleration of gravity at this point. We've gone down by d meters. We are at this point. So if the radius of the Earth is RE, then you know that the radius of this little sphere, I mean the smaller sphere, is RE minus D, isn't it? The whole thing is RE, that is D, so this will be RE minus D. We're trying to find its mass. We're trying to find the mass of that smaller sphere. Density. Density is defined as mass by volume, correct? And what's the formula for volume of a sphere? 4 by 3 pi r cubed. So the mass of the Earth divided by 4 by 3. The 3 goes to the top. That's all I did. 3 goes to the top. The 4 by 3. Okay? So that's the density. Now, mass of that sphere. Mass of the inner sphere. Okay? Will be mass is density times volume. Okay? Density times volume. That's what I've written. Density, which we got now, times the volume of that sphere. This sphere, right? That's why it's 4 by 3 pi times its radius cube. Now it's just math. You got to substitute 4 by 3 pi RE minus D whole cube again times density. Density is 3 times the mass of the Earth by 4 pi RE squared. Cancel the 4 by 3 and the pi. Rearrange. You get this. Is that clear enough? Simple cancellation there. Now, we know that at the surface, I'm writing this again, at the surface it's gm by r squared, or generally that's the formula, isn't it? Therefore, now it is, okay, let me tell you what is going on there. This mass, see, this mass is replaced by this whole thing. Are you with me? Do you watch that? I should have called it M prime or something, but this mass is this whole thing, which you can see here. And then I've got to divide by the radius squared, isn't it? And the radius is RE minus D squared. Okay. Now you can cancel, because there's a cube on top and a square in the denominator. Cancel that, and you get this. And then you say if D is equal to the radius of the Earth. So where are we? If the distance is equal to the radius of the Earth, where are we? If the depth is equal to the radius of the Earth, where are we? Come on. Eh? Remember, we're measuring D downwards, and I'm saying you've gone down equal to the radius of the Earth. So where are you? At the center of the Earth. So in this formula, if you substitute D is equal to RE, everybody knows you're going to get a 0, because this term became, yes, proved. So G at the center of the Earth is 0, proved. Okay, any questions on this? Now answer that question, where does it change faster? Is it as you go up or as you go down? Can you make out from these formulas? Would you be able to draw a graph showing the change as you go up? I don't think I've drawn it, but can you? Can you draw a graph? Try it. Let's see. Yeah, for centuries, moms have been looking at the moon, with the children in their arms and telling them, look, and sing songs, show them the moon and so on. You know that the moon is the natural satellite of the earth, isn't it? And the moon is going around the earth. So scientists looked at that and somebody had to think, hey, if that's going around the earth, why can't we put our own there? With all due credit to the man who first thought about it. Now we have thousands upon thousands of satellites revolving around the earth. But those of you who complain about work and lots of work, please listen to the story. Because when you look at the laws that come by, you think it just fell down from the earth. No. I'm going to give you a story of a man called Johannes Kepler. He was a student of another great scientist called Tycho Brahe. This man studied the motion of the planets for 15 years. Now 15 days, 15 months, 15 hours, 15 years. We didn't even have so powerful telescopes at that time, but this guy would just go every day and say, this is where I see this planet today, this is where I see it today, this is where I see it today. And he made charts upon charts where they are, the locations. 15 long years, he came to no conclusions. But he had a record of all that stuff, and Johannes Kepler was his student. So much I appreciate good students. So he continued the work for another 10 years, using all the schematics and the diagrams that his teacher had. At the end of 25 long years, Kepler came to the conclusion that all planets move around the sun in elliptical orbits. And there's a chill going down my spine. That's what I wanted to say when I say this. After 25 years, you get a statement. And we look at it and say, oh, really? Oh, okay. All planets, that's a powerful statement. All planets go around the sun in an elliptical orbit, which means he should have studied the motion of all planets all the time. That make any sense? You cannot come to a conclusion like, if I say all students are lazy, I'll have to prove that, which means I'll have to study all students all the time. And of course, I'll be proved wrong, correct? You understand? I just gave an example. Kepler's 3 laws. That's the first law that I gave you right now. All planets move around the sun in elliptical orbits. There's a second law and there's a third law. We'll come to that, but before that, we'll talk about satellites. It's so simple. Assume that the satellite is going around the Earth in a circular orbit. There must be definitely a particular force acting on it. What is that force called? Whenever an object goes around in a circular path or part of a circle, we know that this force must act. What's that force called? Centripetal force. And in this case, the centripetal force is nothing but the gravitational force, isn't it? So all we have to do is put those two together. Don't we know the formula for centripetal force? What is it? mv squared divided by r. Don't we know the formula for gravitational force? Yeah, g times product of the two masses divided by r squared. Okay, put them together, you get it. There it is. The gravitational force is the centripetal force. Let me stop it right there. What's the little m? Mass of the satellite, and me is the mass of the Earth. What's r? Is it the radius of the Earth? Nope. No. Radius of the Earth plus the height, correct, plus the height when you do problems. So that is, and then when you rearrange this, you get square root g me by the radius. So what do you say? The further away the satellite is, the smaller its velocity. Correct? And the moon is so far away that its velocity is 1 kilometer per second. 1 kilometer per second. That's not so small, but that's the smallest because it's so far away. Okay, that is the orbital velocity. Can we calculate that? Let's assume that the satellite is very close to the surface of the Earth, okay? So what would this be? If the satellite is close to the surface of the Earth, what is this? Radius of the Earth. So now all three are constants, isn't it? All right, plug in the numbers, get me the value for velocity. Let's see who will get it first. If you give it a velocity, let's say 7 kilometers per second, then you know it's going to fall. Yeah, it's going to hit the surface of the Earth, isn't it? What happens if you give it a velocity greater than 7 points?
Go away.
I thought you would say that because I've heard that a million times, and I'm not insulting you.
Why just keep the same path as
Now you're trying. Now you're trying. It will not go away. But the circular path will become more and more elliptical. Are you listening? So if you increase it to like 8, that will almost be a circular path. But if you take it to 10, then you will see it instead of going a circular path. And if you keep on increasing, when you get to 11.2 kilometer per second, it'll escape from the surface of the Earth. That's called the escape velocity. And in the next chapter, we got to find out why and how we get this number. So I'm trying to say that if you had a fight with your wife,
Does not happen.
it does not happen. And if you could pick her up and throw her, giving that speed,
That's definitely not.
she'll never come back, or he will never come back. Let me be not biased, you know. He will never come back. Or just forget that joke. If you take any object, if you can give it 11.2 kilometer per second, it'll never come back. But that is such a huge speed, isn't it?
From any height or?
Any height. And it doesn't even affect the mass of the object.
But it would be impossible to do it from ground level, right?
And if you could, well, it will never come back. Now, look, the fastest rockets we've only been able to get up to 6 kilometers per second. That's why we need more than one stage for a rocket. We need at least 3 stages. Now, you know why? Because you give it 6 and just don't do anything else, what's going to happen? Come back. So what we do is, when it gets to a certain height, fire the second rocket. And there's an added advantage that the mass is decreasing after each stage, isn't it? So the acceleration would be greater. Is that all this coming in? Come on. Yeah. So that is the satellite. And right. Okay, now we can take down the formula for time period. But why should I even teach you? What do you mean by time period? Time period. Time taken for one rotation. What's the formula? Half of it has already appeared. Time taken for one rotation. Oh goodness, circumference divided by the velocity. All right, what's the circumference? 2 pi r by velocity. We got the velocity, just plug that number in. See, where math comes, I go fast. It's easy. Isn't that the formula for velocity that we got, right? So plug that in there, square both sides, and you would get 4 pi squared r squared, and then you would get r there, so r cube. I'm sure you understood how we get r cube, okay? There's an r squared there, square root vanishes, and this will go to the numerator. So you get r cube. Do you see that this is a constant? All these are constants. So I'm going to say the square of the time period is proportional to the cube of the radius. And that is actually Kepler's third law. The square of the time period is proportional to the cube of the radius. We'll come back to that, don't worry. But what does this word mean? Geosynchronous. What do you mean by the word synchronized? Synchronous, same time. So what is a geosynchronous satellite? A satellite that has the same, it stands at the same position on the Earth. And that is, of course, a communication satellite. I mean, if we send a satellite from here, don't we want it to be over our country all the time? So, don't you have to have it spinning at the same rate as the angular speed of the Earth? Come on. And did I already tell you that the angular speed of the Earth is 2 pi divided by 24 hours? So now you know the time period of a geosynchronous satellite, correct? Same as that of the Earth. So we're going to find the height. I do not remember whether I calculated it, but you could. For a geosynchronous satellite, time period is 24 hours, yes. And the radius, okay, I did not calculate, but you could get it. And you will get it as 4.23 times 10 to the 7 meters. So the height would be about 36,000 kilometers. That is where our communication satellites are. It's not where you can reach it. Hey, come on down. No, it's 36,000 kilometers above the Earth's surface. Isn't even that waking you up? 36. Okay. It's such a height. You got to take it to that height first and then give it the speed that is required. Do we have to give it 7.9 kilometer per second at that height? Or will something less do? Yeah, because this is what you got to give it if it's at the surface of the Earth. Right? Are you getting everything now? So you got to take it to 36,000 and then give it something less, which we could calculate, of course. If you put back that radius here, you will get the velocity. So I can ask you to do any of this stuff on the exam. All right, keeps going. Kepler's laws, last part. 3 laws, Kepler's, and I already gave you the first law. All right. Does anybody remember the first law? All planets move around the sun in elliptical orbits, but an ellipse has 2 foci. Foci is the plural of focus. An ellipse has... Okay, let me draw it. That's an ellipse. There'll be one here, one here. The line joining them is called the major axis. The line at right angles to it, passing through the center, is called the minor axis. Little bit of math. So you have the sun here and the planet here going around. You see? So you see that the sun is at one focus out of the 2. That make it clear? So it's also clear that the distance of the planet from the sun is not the same always. There are times when the planet is farthest. There are times when the planet is closest. Therefore, the velocity of spin will also change. I mean, not the spin, the velocity with which it's orbiting will also change. Just by common sense, tell me, is it going to be at A or B that the velocity needs to be the greatest? I'll give you a clue. The centripetal force is the gravitational force, right? Here, you know, it's very far away. Distance is greater. Centripetal force is, so distance greater, centripetal force is smaller. Correct, gravitational force is smaller. Does that make any sense?
Yeah.
Therefore the velocity could be, because that's a square there, smaller. But here, closest, it's moving fast. Now we know why days and nights do not have the same length during summer and winter. Oh, you don't? All right, you know that the Earth, we're talking about the Earth now, of course. It takes 365 days to go once, isn't it? And you have all the 4 seasons, or if you only have 3, you know what I mean.
Southeast Texas, maybe 1.5.
I don't know. Yeah. 1 actually, it's all summer. Anyway, never mind. So you know what I'm trying to say, correct? Here it's going, from here to here, it'll go really fast. But the same distance here, because it's going slower, it'll take more time. Are you listening to what I'm saying? Yes. All right, actually we're coming to the second law. Kepler's second law talks about, watch. Let's say this planet is here. You have an imaginary line joining the planet to the sun. And then, in a certain time, it goes to this point, from A to B, okay? From A to B. Are you with me? So that imaginary line sweeps out a certain area. You saw that? In a certain time, right? Now let's say after some time it's come to C. And then in the same time that it took to go from A to B, don't you think it'll go a bigger distance here? Yes, and if you take this area, it'll be the same. Kepler found out. That is called the areal velocity. Because it's not distance by time now, it's area divided by time. You see that? So Kepler's second law, the areal velocity of every planet is a constant. Okay. We'll get it slowly, one by one. The path of each planet, that's the first law, the path of each planet about the sun is an ellipse with the sun at one of the focus, or with the sun at one of the foci, depending on what I wrote. This is too slow. Makes sense, doesn't it? Very clear. Second law. Now you can see the areas there, can't you? All right. I'm going to say an imaginary line drawn between the sun and the planet sweeps out equal areas in equal intervals of time. That imaginary line, you can see the shaded part, both have the same area. An imaginary line drawn from the sun to the planet sweeps out equal areas in equal intervals of time, which again means when it's moving from A to B, it's moving much faster, isn't it? If it has to sweep out the same area here, doesn't it have to move faster here? That's it. It's understandable. Everything in physics is understandable, but with a lot of concentration, as you can see, because it's like more concepts coming in after every 5 minutes. Can't help it. That's the nature of the subject. I hope most of you got time to write it. Otherwise, it's in your textbook. The third law. Didn't I already tell you the third law? The square of the time period is proportional to the cube of the mean distance. The square of the time period of revolution is proportional to the cube of the mean distance between the planet and the sun. Between the planet and the sun, t squared is proportional to r cube. I like this. I like this. This tells me, look at this graph. Just take a look at this graph. What do you have on the x-axis? Come on.
Square.
All right, that's t squared, but the time unit is years, right? And on the y-axis we have, what is that? The cube of the semi-major axis. All right, look. Didn't I tell you that this is the major axis? So what would be the semi-major axis? Half of that. That would be the mean distance for sure. Because this is the minimum distance, this is the maximum. Add them up, divide by 2, when you get half. So that's the semi-major axis, same thing. What a perfection. Just look at that. For each planet. How many planets do we have now? One of them was kicked out. You know that, right? So many years back. Anyway. Okay. Wow. What a perfect straight line. Now, do you think all this happened by chance? That's easy to believe. That all the planets started rotating on its own out of a big blast and then got into their orbits and perfectly matched. That's easy to believe, but I'm not going to believe that. Although I have taught science for so many years, it's easier for me to believe, for me, I don't care about you, for me to believe that there was somebody who designed it. That's easy for me to believe. I don't know about you. How did this, we're talking about massive objects moving around, and by chance, they knew at what speed. Oh, goodness. Somebody's crazy out there.